Good evening. This is a recording of Computer Science Paper 1, AQA paper. Now, with this paper, we're going through the Python version of this, where it's option B if you've seen on the exam timetable, which is scheduled for the 16th of May 2022. And first, we're going to go through a few definitions. First, what do we mean by algorithm, abstraction, and decomposition? So I'll give you some time to do this, and then I'll write the definitions. First, the word algorithm means a set of steps executed or followed in a specific order or sequential order to achieve something. We can see these purposes in a few moments where we'll use a few examples of some algorithms. Now, abstraction is where we remove unnecessary detail from a problem. So this is where, for example, when you go into your actual programming questions, you need to pick out what you need to do and ignore everything else that isn't relevant. So for the program to function, you may need to ignore things that aren't relevant, such as font types even. And decomposition also works well with the programming questions because we break down the task into sub-problems. So these two here that we're going to focus on throughout this lesson. Next, we'll go through a few examples of algorithms. And the first type of algorithm we need to look at is the searching algorithm, where we try and search for something in a list, which in this case, we'll use a number. Now I want you to find the number 45 in the list below. Pause the video if you like. Now how did you find it? The most common way could be to start from the beginning or the end of the list, but really, the method for this linear search is to start here and check is it equal to 45. It isn't, so we move on to the next number. It isn't, so we move on to the next number, which isn't, and so on, until we find 45, which we found it, and we end and continue, because we found what we want. So this can easily be a loop, where we compare each element, one after the other. Now the next method of searching for a number is binary search. Here we have a big list, and again, I want you to find 45 using binary search. And we just need to list the comparisons done to find it. So that's a common exam question, really. So to use binary search, we use the median, which is the middle number when the list is sorted. So for example, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. so far. And the median falls in between the 6th and the 7th. So right here. If it falls in between two numbers, we take the average, 45.5. So that's our first comparison. Is 45 equal to 45.5? No. And then we check if it's greater than or less than. So you have to be consistent with your comparisons. I'm going to use less than. So is 45 less than 45.5? Yes. So that means we get rid of the top half of the list here. And this saves time, which we're going to see when we compare the searching algorithms, because we do not need to search this half of the list here. And then we rinse and repeat the process again. We find the median of this bottom half, and this will end up being 34.5 for the median. So we first check if it's equal. Is 45 equal to 34.5? Nope. Is 45 less than 34.5? No, it isn't. So now we get rid of this half of this smaller list. We get to this new little list here. That's the median, 37. The middle number, we check again if it's equal. Nope. Is it less than? Nope. So you also discard the median itself and everything below it. And we just happen to be left with 45, which is our number. Now if we compare the two algorithms, we can see that binary search is much faster. This is because we discard halves of the array. While linear search is slower, especially on the longer lists. Now here's something we might get to with sorting algorithms. If you were to study computer science past GCSE, you may look at how the time increases or varies as we increase, for example, the size of the array. And then you'll see things called the best and worst cases. So best case, for linear search, it can actually be faster than binary search if it's the first element. Whereas the best case for binary search is it's the median. Whereas the worst case for linear search is it's the last element. And it's usually on a long list. So they have to keep going through every single one until it reaches the end, and that's a lot of time wasted. Whereas with binary search, well, it's not found until the end. Which is like our example. And this happens to be quite consistent, but is consistently fast. Another thing about each of these programs is not really the time, but how easy it is to program. So linear search, as I said, was just a loop where you just compare one after the other. Now this is actually quite easy to program and implement. Whereas binary search, you'll have to use the median and discard lists, or half the list. and this is harder to program. And if you didn't notice, the median requires the list to be sorted, so binary search only works on lists that are sorted. Whereas linear search can work on unsorted lists. So those are your three things you need to remember when comparing these two algorithms. Next, we'll look at sorting algorithms. Bubble sort is our first one, and we'll use bubble sort to sort this list below. So what we do first is we start at the beginning. This time we compare two numbers. Now, we know that the wrong way around if the first number is greater than the second number. In this case, they need to be swapped around, so 10 goes before 31. Our program could easily do this by comparison. It'll just swap it around. Then it'll shuffle along one and compare 31 to 25. It will compare these and swap them round if they're in the wrong way or the wrong place. In this case, it does. Now 31 is compared with 35, so it shuffles along again. It's okay. It's in the right place. Now 35 with 39 in the right place. And 39 with 34. They're the wrong way around, so we need to swap them. As 39 continues on, and it brings us 33 here. And compare, swap them round. And finally, compare with 32. And swap round again. Now you can see that the largest number in our list has reached the end. And we basically repeat the whole process until all the numbers in the list are sorted. And we can tell the list is sorted if no swaps are made. That means all the pairs of numbers that we checked are already in the correct order and it's sorted. The other algorithm you need to know about is merge sort. Now we've got the same list again, and we'll use merge sort to sort the list. So merge sort uses something called a divide and conquer strategy. So first we divide the array or list. So we keep dividing it in half and half again, and then half again of each. So we get these mini arrays that are just size of one each. And then each bit is conquered. So now we put them back together, and that's where the merge bit comes in. So we merge the lists together. So we start with 31 and 10. So merging two mini lists of length 1 each is very easy. It's a simple comparison. So these two will make a list with two numbers in, 10 and 31. This one will go here, 25 and 35. These two go here, 34 and 39. These two go here, 32, and 33. Now, when we combine lists that are multiple numbers long, like these, into larger ones, to make the new list, we compare the first element of each list, or the first number of each list, and we remove the smaller one. So in this case, it's 10. We get rid of it and put it into our new one. Now 31 is our new first number in this list here on the left, and we compare it to 25. 25 is smaller, so we remove it here, and we do the same again, and we can see 31 is smaller. Now we're just left with 35. These two lists will combine like this, so we'll compare. We get 32, cross that off, 33, cross it off, and since we've got rid of one bit of the list, we can just add the rest. So we've got 34 and 39. And then to put them all back together into our original single list that's 8 numbers long, we compare the first two, remove the smaller one, 10, 25, 31, 32, then 33, then 34, 35, then 39. And that's now sorted. And once again, you need to compare the two algorithms, bubble sort and merge sort. Now, in terms of running time, as we can see, merge sort is faster on longer lists, whereas bubble sort is usually slower. And we reintroduce our best and worst case scenario again. Bubble sort can sometimes be faster than merge sort, so it's faster, its best case, when the list is already sorted. What it'll do is just run through the array once, it'll see there's no swaps have been made, and it knows it's already sorted, so that's it. So it's gone through the array once, whereas merge sort will still go through that whole process of dividing and merging back together again. Best case are really the same. So merge sort always divides and conquers, or divides and merges. So this means it's actually quite consistent. Whereas the worst case for bubble sort is that the list is in reverse, or a descending order. In that case, every pass, only one element would find its way to the end where it should be. So on the first pass, the largest element will find its way to the end. After the second pass, the second largest, and so on and so on and so on. So swaps are made several times, and you need to go through the list as many times as their numbers, and that's very slow. So overall, bubble sort is just slower. And again, the slower algorithm is actually easier to code because it's easier to understand. Whereas merge sort is also harder to code and harder to understand. And a few things you may want to consider is when we merged with merge sort, we had to merge into like a new list, so like a new copy. We had to combine the two, first of all, like numbers into one list with length of 2. So that's basically after each merge, we had to copy the entire list again. So actually, merge sort uses more memory. So it's like pick these numbers up and then we put them into a new list again and again and again. So this is like called merge sort out of place. Whereas bubble sort really only needs the list itself, so it uses less memory. The next thing we need to look at now is actual programming stuff. So how do we go about programming? But first, we need to look at data types. When we use data in algorithms, they can be an integer or a float. So these are the two numbered data types we need to know. So the integers are whole numbers. And they can be positive or negative. So things like 42, 9, minus 18, and so on. Floats or real numbers are just not integers. They'll have decimals. So like 0.5, 2.3, and so on. The next two data types we need to look at are strings and characters. So these are both to do with text. So these are really text. So strings are made up of characters, but characters are basically letters, numbers, like as text. This can include spaces and symbols as well. And if you code in Python, you will often see them within speech marks. And if you're on a computer itself, it will be highlighted in a nice green, like this. So like string. So this string here says string, or has the text string. And then the last one is a boolean, which this can store basically a true or false. This can be from a decision to like a comparison, which we saw, like if something is less than another. And these are often highlighted in orange if you could program on computers. The next thing we need to look at is also the operations. So this is how we handle numbers. So we have the basics. From maths, you should be familiar with addition, subtraction, multiplication, and division. Addition and subtraction have the same symbols. So that's your normal plus and your normal minus. Multiplication, however, is an asterisk or a star. It's like where you put notes on something or at the bottom. Division is just a simple slash. It's like how you might write 1/2 as in 1/2, like this. Other ones you may need to know is about integer division and the modulus operator. So integer division is the whole number of times something can fit into another. So it doesn't include decimals. So for example, this is represented by 2 slashes, and if we do something like 18 integer division 5, like this, we know that only 3 lots of 5 go into 18, so that is 15. And that can't go any higher, so that really is just 3. Whereas the modulus is represented by a percentage sign, and this works out the remainder. So what remains after integer division? So if we use the same example, 18 mod, this is written in pseudocode actually, 18 modulus 5, that would also happen to be 3, because back in prime school perhaps, you may have written 18 divided by 5 as 3 remains a 5. I mean, 3 remains a 3. So the 3 lots of 5 and just 3 left over. The last thing you may need to know are the comparisons, which helps with our sorting algorithms. So just like in the real world, greater than and less than are just the same. So greater than is this, less than is this. And remember that if you could think about this as a crocodile, the crocodile will point open towards the larger number. And equal to, not equal to. In the real world, you'd add a little line just right here, like here or here. However, if you're coding in Python, you'll simply need to add an equal sign just after the greater than or less than, like this. So greater than or equal to would be this, less than or equal to will be this. Equal to, if we're comparing something, if, for example, a variable has a number and if we want to see if it's equal to 5, we would use actually two equals and we'll see why. Whereas not equal to is written as this in the real world, but in Python it's this. So it's you have an exclamation mark and an equals. So it's not equal to. Next thing you'll need to know are the variables and constants. So variables and constants are a way to store data. So we first declare it and assign a value. An example could be, for example, a variable I'll call score. So this is called the identifier. And it's good to have the identifier's name as something with a clear purpose. For example, score will keep track of a score. It's better than, let's say, writing just the letter S as the identifier, because when you come back to the program, you won't know what it is unless you have comments. And then we assign it by putting a single equal sign, that's what it's for, and assign it a value. We'll assign it a number, like an integer, like 0 for now. Now with variables, they can be used later in the program. For example, a common way for scores could to be changes by adding to them. You could commonly see it as score equals score plus 2. This adds 2 to score. So the variable score, it still exists. It's a assigned score, which is original value here 2, like 0, and then adds 2 to it. So therefore it adds 2 to the score. And they can also be changed as seen. Now constants are kept constant and they can't be changed. And they are represented by capital letters in the identifier. For example, tax is a very good example of a constant. It's kept the same unless you move up a tax bracket, but it's a good example. Tax equals, let's say, 0.2. Now we can use constants because like they need to stay constant. They don't need to be changed, and it's good to keep them like that because sometimes you don't want to accidentally change them. For example, tax. The next thing you'll need to know about is inputs and outputs. So these are a way to communicate perhaps with the user, the program. So many algorithms will ask you for a user input if you want to input something and store it often in a variable, as well as an output, for example, if we want to tell the user to do something or tell the user the information. Now, to input something, this is the commands right here. Just simply input. And remember that all these commands or functions are always written in lowercase. So for commands or functions, always write in lowercase. This is important because you will lose marks if you don't. Next is the output, so to print, it will print whatever is stored inside this bracket here. And the good thing to remember as well with brackets, for every bracket you open, so this is like an open bracket, we need to close the bracket if you like, so add to make a full pair. Otherwise, your program will have something called a syntax error, which we'll look into later. Now, prompts are just a way to ask for print statements. So these will tell the user what to do. For example, to input something. An example of this can be, first we ask to print, and we'll print out, let's say, enter your grade. Close it off with speech marks. This works the same way as brackets as well. So if we have one set of speech marks at the start, we must close it off with another set of speech marks at the end. And then we can have an input and this actually should be assigned to a variable. So we state the variable first, and we'll choose an identifier. Let's say the identifier will be my grade, like this. And we'll sign it with an equal sign. We'll sign it to the user input, so the input, whatever is inputted from the user. And as a final note, if a user inputs something, they type something on the keyboard, by default, the input is a string. And bear that in mind because you may need to change this data type for it to work with calculations. Now, next data structure you may need to know about, which we haven't looked at, is actually lists. Variables can also store lists, like this. So we have the identifier example, assigned with a list containing the integer 4, string 8, a float 15.0, a boolean true, another character, t, and then the number 42. Now, what do you notice? You can clearly notice that you have different types of data. This could be good because these could all be related to the same thing. Lists could be a good example of storing settings, such as if you want a certain color, for example, if you want something to carry out something automatically, this could be the true or false bit, and so on. Now, a way to print out one of these elements of the list or items in the list is by using indexing. So that's how we can tell one thing is separate than the other, other than the comma. So each item is assigned an index and it starts at 0. So with the number 4 here, we'll have an index of 1. So that's like the first number in the list. And this string here will have the index of 1, then 2, 3, 4, 5, and then so on if we could add some more. Now, I've got the command print, and then it's going to print whatever is in here, and we're just going to look at this. Example 1. So that's how we try and mention one of these indexes. So we have the variable name, which has the identifier example, which is here. And then we have the index number 1. And that is just this string 8. It will print that out. Therefore, this will output 8, the string 8. Now, when we work with strings as well, we could do things like concatenation, indexing, and substrings. Indexing we're already familiar with. This works the same way as lists. And this is instead not broken down into each item in the list, but rather each character. So let's say I have the variable um, comment, then I assign it the string excellent. Indexing literally just works the same way. So indexing again starts at 0. So this is the index 0, x would be 1, the letter C would be index of 2, the letter E next would be index of 3, 4, 5, 6, 7, 8, and so on. And we can just print each index in the string. For example, the function print comment, and remember that we put indexes in square brackets as well. You can add that to your notes. If we put, let's say, 3, it'll print out the third index in this string, or the third, or the rather actually the fourth character, because we add one, the indexing starts at 0. This will output E. Our concatenation we could think of as ends of tape. So let each string could be the bit of tape like this. If we wanted to add on another string, like but then, to bring the two together, we concatenate them together. So we do that by putting a plus sign. And then substrings also link into indexes. So substrings is just one section or one portion of the string. For example, again, we could print out a section of this string stored in the variable comment. We could start at the index 0 and we put a colon, and then the index we're just finished before, so like 1 before it, and we'll end just before 5. This will print out indexes 0, 1, 2, 3, and 4. So overall, you'll get printed out E, X, C, E, L. That's it, those 5 characters there. So this is kind of like a range or which indexes to print out. The next thing you need to look at are conditions, or Boolean logic, which links into logic 8 with paper 2. Now, if we have a not, this means anything that's false becomes true, and anything that's true becomes false. For example, we could have the very obvious comparison. Let's say, is 5 equal to 5? This would be true. But if we put a not around this then overall becomes false. Because this is a bit like saying, is 5 not equal to 5? No, it isn't. The next one you need to look at is and. So this only returns true if all multiple statements are true. For example, if you have one statement that is true and another that is false, that just returns false. So if it's false and true, both aren't true, so that still returns false. But if we have, let's say, true and true, this returns true. The last thing you need to look at is the or statement. So this is true if at least one is true. One of the statements are true. So in this case, if we have true or false, this would become true, false, or true. This would also become true, true, or true. This could become true. For example, if there was a statement, I will find you, or I will beat you, if either of them are true, the whole statement is true. Next thing you need to look at now is selection. Selection is where, depending on the condition that we looked at, for example, if a variable is equal to 1 or greater than, whatever you like, or what is required based on the question, we could use an if, elif, and else statement. So here is the whole thing. What happens here is when the program reaches here, it says the words if. Now we looked at this statement. If the statement returns true, these instructions will be carried out. So I'll write true also, rather a tick. And then after that, it just continues on with the rest of the program. So this is a bit like in a flowchart style. If the statement is false, it goes here. Then it looks at this statement here. Once again, if it returns true, these instructions instead, which are indented, if you can't see, like which are moved across a bit of space, these will be carried out. And then, after those instructions are carried out, it exits and it continues with the rest of the program, following down just right here to the bottom. Again, if this statement isn't true either, it will go to else, though really it can go to another elif statement and so on, but these are really if none are true. So else is like a last resort really. If any of the above aren't true, this will be carried out, and it'll just carry on with the rest of the program. Suppose this could be used to check the age of a person, like age restriction. I could write the first if statement to be if, let's say, we have a variable called age which stores the user's age. Age is greater than or equal to 18. Let's say we'll print out let's say authorized. We could have an elif statement. Let's say if the age is instead greater than or equal to 16, we'll print out something else. Then else at the end if none of the above are true. We'll also print something out. We'll print out that string right there. And that's an example of an if, elif, and else statement. So we should only really use one if statement, then as many as you like of the elif statements, but really they shouldn't overlap too much. And the else you can only use once. And all of them aren't really needed, but you just need, this is the minimum. You need at least an if statement. You can have an if statement and then not have anything else. That's actually, that only can work well. It works. You're allowed to do that in a program. These are really here optional. The next thing you need to look at is iteration. Now we have some for loops. Now why is this? Right. Now here's the first task of the night, or whenever you're watching this. So to create an algorithm that generates the Fibonacci sequence. So the Fibonacci sequence is generated by adding the last two terms to produce the current term. So first two terms are 1 and 1, and you should get the sequence 1, 1, 2, 3, and so on. Because these two here are added to get 2. These two here, 1 and 2, are added to get this. These two, 2 and 3, are added to get 5. 3 and 5 are added together to get 8. And so on. So this kind of repeats. So this is where we can use a for loop. So these are written in for I in range. So we'll use this as a bit of a startup. So for means we go through a loop, and I is just a little variable here. And I will start at 0 and then go up one by one until it reaches 6. So when it reaches 6, the loop is like stops and it carries on with the rest of the program. And remember, it doesn't go through the loop when it is actually 6 itself. Because also I will go from 0, 1, 2, 3, 4, then 5, and then exit the loop. So just before the 6. What we could do here is part of the solution. We could use this I here to determine the index. So let's say we already had a list earlier, so we have this variable with the identifier sequence. We'll assign the first two numbers of the Fibonacci sequence, just 1 and 1. 1 and just 1. To generate the next sequence, which in this case, so this would be index 0, index 1. We want to, in the first bit of the loop, when I is 0, we want to generate the second index. So sequence I plus 2 is equal to the previous two indexes. So it'll be I itself plus the next one, which is I plus 1. Because remember, when we add a number onto an index, we go to the next item in the list. And that's really all you need. And then at the end, you will just simply print out sequence the whole list. It will then print out that whole list, so 1, 1, 2, 3, 5, 8, 13, 21, and so on. So that's the final command, really, to get this last mark. So this is called definite iteration because iteration just means loops or repeating. So it repeats a finite number of times from 0 to 6. The next type of iteration we're looking at is indefinite iteration. So where we use something called while loops instead. Now, while loops work almost a bit like if statements. So the while loops depend on a condition if it's true. Now here's an example. To show how while loops work, we'll need to label a few things. Now, if the statement here is true, this highlighted statement here, if it's true, all these instructions here are executed, and then it will go back up again. However, if the statement isn't true, it will exit this loop and continue with the rest of the program. So basically, this loop keeps repeating until the condition is false. And as you can see here, since this condition here is literally true, it returns true, it'll go, if I use a highlighter, first to here, then back again, and then since it's still true, it'll go again. So what we get, if you haven't noticed now, is an infinity loop. So if we put this into a program, this will continually print the string message on each line because it's repeated. And the reason why it's called indefinite iteration because it's hard to tell when it will stop. Next thing you'll need to look at are subroutines. Now, think about something you do, let's say, every day or frequently. Is there something that triggers it? For example, waking up is something you have to do every day, and it could be triggered by your alarm clock. How would we do this with machines? For example, waking up, if you break that down by decomposition, you open your eyes, then possibly turn bits of your body, such as you physically using your muscles to get up, but you don't literally think all of that. You just think, get up, and you do all those automatically. The problem is we can't do this with machines because with machines, they do what we literally tell them to do. An example could be cake instructions. We can't just tell a random Python interpreter just to say cake instructions because it does not know what we mean by that. And we can tell it what we mean by defining what this subroutine is, or procedure perhaps. So procedure has to be written like a variable. So this is our identifier or name. So this again needs to have a useful name. So cake instructions, its name has already a purpose to print out the cake instructions. For example, it could be just print out this string here, sift flour, and another string, add detergent. It's now the computer actually knows what we mean by the subroutine, but we haven't actually called it out yet. To call it out, what we'll need to do is to write the subroutine itself, cake routines, or cake instructions, and then the two brackets. And then when the computer sees this, it knows what it means, so it will do these instructions whenever this subroutine is called. Now this is called a procedure, a type of subroutine, because it doesn't return anything. That's the keyword. It doesn't return or output. And rather, this should say an input. Rather, return is based off an output. So we input something, do something with an output. So that's what makes something called a function, which we get into. Now with parameters, we're going to think again of our cake instructions. Now, think of your procedure again or task, or you can think of cake instructions again. How could the task change slightly from time to time? Is it always going to be adding flour? For example, will we need to be a bit specific with the flour? Maybe. Could it be done multiple times or for others? And therefore we take into parameters into account. So the parameters are a way to change the way the subroutine works. So this little letter here is the parameter, and it's used a little bit like a variable. So whenever you see this little letter again, it's where, for example, let's say if there's a number here, this number gets used here. For example, we've got a variable inside this subroutine. This is actually called a local variable. It only exists when the subroutine is called. Then we have another command just to print out, and we notice that we concatenate this a string from a flour. So how many grams of flour we need? We need the string bit here because we could these pluses here, these concatenations only work with strings and other strings. So for example, if we call a subroutine again and say cake instructions, and then in the brackets we have 3, what we will do is flour, the local variable, it'll be assigned the value 100 times whatever is in this bracket, 3, because remember this 3 comes down here because of the parameter. And then as a result, it will print out the string sift 300 grams of flour. Whereas let's say if we put 5 instead, it would say 500 grams of flour. So this is a way to adapt perhaps your subroutine. Next, we look at functions, which I mentioned. So it's different to procedure because now it has an input and an output. So it will like return something. Now return is actually a function or a keyword in Python, and it's often highlighted in orange. Now, Python already has some of its own functions, such as the length function. This figures out the length of a string or a list. So this here is also our input and a parameter. So for example, let's say we have a variable again, which we'll use comment, has the string excellent. If we do the commands, let's say len comment, so we'll look for this variable with the identifier comment, which it finds here, and it sees a string, and that's okay. Then it will return, so this will be like your output. It will return how many characters there are in this string excellent. So there'll be 1, 2, 3, 4, 5, 6. So which will return 9 because this is like 9 characters long. So you can see this is a function because we have our input and our output. Now, why would we use subroutines? Now, do you remember at the start the word decomposition, where we break down problem into a number of subproblems? Now, the good thing about that is we can have several subroutines, each with a different purpose, which are all clear. For example, you could have one subroutine to keep track of score or adding it. You could have another subroutine to keep um, track of perhaps a game that's going on or a sorting algorithm that's going on. Now, as a result, if we use this structured approach where we break down the problem into subproblems, the code is easier to maintain and debug, correct, change, whatever, because we have a define, the subroutine, and then our code here, and we just call the subroutine again. If for some reason we need to change the subroutine, like if there's an error, we only need to change what's in here. Whereas if we used just normal code, if we have an error, let's say this code is used 100 times, we will have to change that same piece of code 100 times. And that's not efficient. that time could be better used elsewhere, such as for developing the program. Another advantage could be to simply use local variables, which make sure things within the subroutine themselves don't get confused elsewhere and stay relevant to the subroutine only. Next, we're going to look at programming errors. Now, if you code on a computer, you'll often run the program to see if it works or really to just check if there's errors, if it's right. There are three errors you can find. First is a syntax error, a logic error, and a runtime error. First, we look at syntax errors. Now, we have some code here. Now, why won't this program work? I'll give you a few seconds to figure this out. Pause the video if you like. I'm just going to say the answer immediately, and I'll highlight it. So the errors are here and here. So syntax, if you look at the meaning, just means like the language, or rather how we order things. So how things are written. So this is the best way to explain a syntax error. For example, as I said, all of these functions need to be all lowercase. If we have even just a character that's uppercase, like this capital P here, the program literally does not know what to do because it does not have a function with this exact name. Whereas here, it's missing a bracket because you need to have the same number of brackets opened as closed. So really, when it looked at this code, it thought it was expecting something else here, like, for example, the concatenation. But it didn't know because there was no bracket to end whatever was going to be printed. This program simply won't work because the computer doesn't understand it. The next thing you need to look at are runtime errors. So this is where the syntax works, but it still won't run. For example, it will crash at a certain point because whenever you reach an error, like a syntax or runtime error, the program will just stop because, again, the computer doesn't know what to do. Now, here's an example. One of them could be something that doesn't exist. For example, we have the list with the list assigned to it with four numbers, 2, 5, 8, and 4. We'll just label the indexes right here. So we start at 0, 1, 2, and 3. So we have the indexes from 0 to 3. Now let's say the command comes after to print out the 6th index of this list. Computer doesn't know what to do. The syntax is okay. It's all lowercase. The variable is meant correctly. We're using square brackets. But it's just this bit here. It doesn't understand the 6 because the 6th index doesn't exist. It only goes up to 3 and that's it. So it doesn't know what to print out and that's an error. Another thing could be an incorrect data type. So we have some more code here. So we first have a constant which is assigned an input. Then this another variable will try and double this and then print out like what's stored in the variable double. All the syntax is correct. They're all lowercase for the inputs, prints, string, and so on. It's concatenated rightly, but not everything. Because, for example, what if an idiot tries to input a string into this here, like yes? What does yes, the string here, then if we multiply it by 2, what does this mean? So really, if you want to input as a note, if you want to input an integer, what you really need to do is to cast it, so to change the variable or data type. So what we do is we put int in our input, because remember, inputs by default are strings, because it's typed from the keyboard. Now the last error we need to look at are the logic errors. Now we got this program below. Once again, think carefully. So the program works, there are no syntax or runtime errors, but it doesn't work as intended. Now why doesn't this work? So let's say the user follows along and the user will be asked to enter a number first. Let's say we will enter 3, and that's stored in this variable, num1. We're asked again to enter another number, let's say 4, and that's stored in this right here. And then these two are added together and stored in the variable sum. Now this is where the error is, because remember, inputs by default are strings. The plus number, the plus symbol still ironically works with strings, because remember, it concatenates them together. So if we combine the mini string 3 and then 4, then we just add them together, they just literally combine as they are to put 34. So at the end, it's going to say the number of the sum of 3 and 4 is 34. The program works, but not as intended. Now, how can we avoid some errors? So first, for syntax, really, is to either debug the code, but unfortunately you can't do this in the exam. You can't have a computer in the exam. So usually you'd try and read through the program again, whether you've typed it or just written it on paper. And again, and I say this again, make sure functions like print, like all lowercase, and to have the same number of this bracket as this bracket here. So you should have pairs of brackets all the way through. The next are the runtime errors. Again, you could just run through the program with trace tables and think about using validation as well to make sure that you can't accidentally go into an error with something that might not exist. Same could be said for logic errors, where you run through the program with trace tables. And again, you might think about using validation to make sure that you don't want data that's too large or too small, for example, with numbers. For all there is, just try testing with different inputs. Now, validation is a common thing that is asked for in exam questions. So this involves checking if an input is fine to use in a program. For example, user will input an integer, and we need to create an algorithm that will check if it's greater than 15. And if it isn't, like greater than 15, we want to keep asking the user to input the new integers until this condition is met. So we need to keep asking the user to input a number until it's greater than 15. And if we need to keep doing that, and we can't really tell if they will, we need to use indefinite iteration, like while loop. And first, we start off with a boolean stored in the variable valid. Right now, we'll say it's false because we'll have a loop, and while the variable valid is false, so while the condition is false, like it's not greater than 15, all the code below that's indented slightly will be run. So first we'll ask the user to input a number stored in the variable check, and we'll use an if statement to check if it's greater than 15. If it is greater than 15, the code indented in the if statement will run. So that means valid equals true, so it changes the variable valid. Otherwise, it remains as false, and we come to the end of these instructions here. And it will go back here again and check if the variable valid is still false. If it isn't, it'll continue here, keep asking again. If it's true, exit the loop, continue with the rest of the program. Now, an extension of validation could be for data types. So this is like another layer. So in some of the examples, like the past one, the program will crash. This will be like a runtime error if the user will enter, let's say, a string instead of a number, because you can't compare a string with a number. And it will cause something called a value error. So an example two, this is optional really. So a second example would be creating an algorithm that keeps asking the user for an input until an integer is entered. So ideally, we'd still have that valid is false, and then our for while loop again. This time we have something called a try clause. So it'll try this lot of code right here. We're asked to enter an integer, and which is then our input is stored in the variable check, and then immediately we have the variable valid changed into true. Now we have this except clause here. So if at any point when running this code there's like a value error, for example here, when there's a string inputted instead of an integer, so if any errors, it will go down to this here and then run the instructions here. So for example here, if the string is inputted, then error will occur. This code will stop here and go to the except value error bit. So the valid bit will remain false, and then the end of the while loop is reached, so it will check again. Once again, it works the same as before. If it's false, it'll continue and try again. If it isn't, it'll go to here, it'll just print out valid, and we know the program will just continue with everything else. And the reason why you don't need to do this is because usually in the exam questions, it will say that you should assume that the user will input an integer already. You don't need to do this often. Now, validation task for you. So you try and practice this. So we're going to ask the user to repeatedly enter a number or integer until it's between 10 and 50 inclusive. And we'll just say, for the sake, you may assume that the integer is being entered. So we'll use our while valid equals false model. So we'll first declare our variable valid, and we'll assign this the boolean false. Now we'll have a while loop. So while the boolean stored in the variable valid is equal to, so remember we need a double equal to for comparing. We'll indent this now, so we'll first ask the user to input into a variable called check. And remember, we'll need to cast this. So we first have our input, but we need the int around it because we need to change the data type from a string, which is the input, into an integer for the rest of the program to work. And we can assume anyway that an integer is being inputted. Now we're going to check itself and see if it's greater than 10 and less than 50 inclusive. So we're going to use less than or equal to and then greater than or equal to. Because we're going to have actually two statements and we need both of them to be true. So we're going to use two statements with an and between them. Because remember, if we have an and statement, it only returns true if all statements are true. So we have an if statement. So if the whatever's stored in check is less than or equal to 50 and is greater than or equal to 10, then we can say valid now is true. Otherwise, we'll put an else statement. So if the thing above isn't true, it still remains false. Now, the last thing we looked at is testing for errors. So here's some code from earlier. Now, how can we test this program to see if it works as intended? Like, if we have a compiler in actually ourselves, like to input values ourselves and run the program on a computer. So testing data, but first we have the normal data. So this false needed to work as intended. So this will be the data that should work as intended for this. So let's say 20 should work, 18 should work. Those are a few examples of normal boundary, normal data like data. So boundary data now is may or may not work. So it's on the actual boundary here. So we can test, let's say, 15. 50 is on the boundary, and then 16 as well, which is the last or um, piece of data that returns true. So this is like on the boundary. So this can check for like the greater than or equal to, or just the greater than, if we want to let it work as is. And the last one is erroneous. So this would be data that we expect to not work, such as let's say -8. So that's far from the boundary. There could be even the wrong data type, like a string, and we still know that it just won't work, and that's okay. The last way of testing the programming is through trace tables. So here's some code. We have a subroutine where we have some inputs and outputs. So that's our return bit. So this is actually a function. So we complete the trace table, which is to our right when the subroutine call total out 3, 4 is made. So here's our trace table. Now, when we call this, if you write it similar here, you can see that A is our first number, A is our first number, then B is our second number. So that's our first few values already. So A starts as 3 and B is 4. And then when we run this, we have a local variable C, and that's assigned the value of A plus the value of B. So 3 plus 4, the values of A and B respectively, that gives us 7. Now we're going to enter this while loop. Then first comparison we need to make is A less than C. So A right now is 3 and C is 7. So that returns true. So we're going to go to this bit of code here. So A is assigned its original value found in A, so that's 3, plus 1. So it increases by 1. You only need to write a number again in a column if it changes. So if it stays the same throughout the algorithm, you don't need to write it again. And then when you run this line here, B is assigned its original value, which is 4, subtracted by A, which is now actually 4 right now. So it decreases by 4, which is 0. And then it loops back up to here, checks again if A is still less than C, 4 is still less than 7, so it goes again. This we already know increase, this is A by 1, this subtracts A from B. So A is increased by 1 again to 5, then B, like A is subtracted from B, so B is decreased by A now. So B is decreased by 5, so now it becomes minus 5. Nothing happens to C again. And we get to the end here, and we loop back. Is A still less than C? Yes, it is. 5 is still less than 7, so it goes to 6. It'll then decrease by 6, so minus 11. Loop back again. Is 6 still less than 7? Yes, it is. So it's going to run through the loop one more time. So A is now 7. B will decrease by 7, so minus 18. And loop back up again. Is now finally 7 less than 7? No, it is, because it's the same, it's not strictly less than. And then it will return B, which is minus 18. But we don't need to do that because we've just completed the trace table. And remember, you won't need all the rows. Now we're going to finish off with some practice questions. Now, first we have some code. And this tries to find the highest common factor of two numbers. Now, the highest common factor is the number that can divide into both numbers without leaving a remainder. So it's like divisible by both numbers. So for example, if we input 4 and 6 into num1 and num2, at the end, the print statement will return 2, which is correct. However, the program doesn't work when 4 and 4 are inputted, which returns 2 rather than 4. And the first part, so part A of this question, is to use a trace table to show that the program doesn't work when 4 is inputted for both num1 and num2. So I'll actually add num2 in another column, but we don't really need it. So as we know from the question, 4 is inputted into both. Now we get these lines here, so a variable HCF is declared and assigned the value 1. The count is declared and assigned the value 1. Then we enter this while loop here, where we check if the variable count is less than the value of number 1. So that returns true, and it enters this little section of code here. Now we check, now this is actually a modulus operator, so this checks, all this here checks if divisible. So for example, num1, so that's 4 right now, modulus 1, which is a count. So 4 divided by 1 is 4 exactly, so no remainder. So 4 modulus 1 is 0, and that's true. This is also true. So we'll go to this little bit of code. Now the HCF, highest common factor, is assigned the count, which is still here. It doesn't change, so you don't actually need to write this. And then it can just continues. And then the count is assigned its original value plus 1, so it increases to 2. We go back up again since the code within the while loop is finished. We head back to the comparison again. Is count less than num1? So is 2 less than 4? Yes, it is. So it's going to test if 2 is divisible into both numbers. Yes, it is. So HCF is now updated to 2, so its count is increased by 1. Count is still less than num1, and it then finds out that if we divide 4 by 3, we get a remainder that's not 0. So it increases the count again. And goes back to the while statement. So is count, which is 4, less than num1, which is 4. It isn't anymore. So it ends this while loop and just prints out what is in HCF, which is 2. So it prints out 2. Right, that's what it means in the question. And this doesn't work because actually HCF, the highest common factor of 4 and 4, is meant to be 4 because 4 divided by 4 is 1, remainder 0. So something wrong is wrong with the program here. And we'll just practice a few definitions again. We've got the code again, and part B, I, is state the line number where selection is used. And usually you'll have the line numbers written on the margin on the left here in your exam paper. So unlike me, you don't have to write it down. And remember, selection is where we select some statements based on the condition. So that's usually an if statement. And then we state the line number where the if statement actually is. So it'll be line number 6. Part 2 of B is state the line number where casting is first used. So casting is where we switch or change the data type. If we look through the program, it's actually on line 1. Because remember, input is a string, and then on the outside we have int, so we're actually changing from a string to an integer. That's changing the data type. And part I is what type of iteration is used. Now, the type of iteration that used is within this while loop here. And see, we can have a condition here. So if you have a condition, this is indefinite. And then you just need to know that. And that will be part C of the problem. So I'll write out the code here again. Now, state the line number which causes the problem described. So remember when we put 4 and 4 into the inputs of num1 and num2, we get printed out 2. And we know that the HCF of 4 and 4 should be 4. But if you remember, we had this count so that tests all the numbers from 1 up to the num1 if it's a factor. And what it didn't do is let it go equal to. So this is actually the line number where it's the problem. So 1, 2, 3, 4. So line 5 is the problem. Now we're going to rewrite the line of code that you stated, which is a problem, and solve it. So we saw that it didn't let or didn't test if um, num1 was a factor of both numbers. So we're going to let it go up still, but we just need to change that it can allow if it's equal to, so if count is equal to num1. So it'll still go 1, 2, 3. So it originally it tested it if 1 was a factor, if 2 was a factor, if 3 was a factor, and it stops there. This time we need to test if 4 is a factor, so we need to allow if while count is greater than or equal to num1. And part D is now the code is used to define or create a subroutine named HCF. Now, why would num1 and num2 right here be parameters? Now, because these are inputs, and really they affect how program runs. Now, explain why it's an advantage to use sorry there to use subroutines when coding. Now, we said before that it helps with the structured approach. So the code is also easier to maintain, because you only need to change the define bit or the define section rather than every time the same instructions are needed. And you could argue as well, it's easier to write code simply, which is like where you do the same task over and over again. Now, here's some actual programming practice for yourself. So write a program in Python that simulates a children's game called FizzBuzz. Now, this is the game where we count up in whole numbers, starting at 1, 2, 3, 4, and so on. Now, the program should first ask the user to enter an integer until it's between 70 and 200 inclusive. So that's actually validation. So you should get that from your notes as well. That's the while valid equals false, if you remember. Then output the numbers from 1 to what the user asked for. So it could be 1 to, let's say, 100. And this would really be a for loop. But if the number is divisible by 3, so if it goes through the numbers and it reaches a number that's divisible by 3, it should output the string fizz instead of the number. If it's instead a multiple of 5 or divisible by 5, it should output buzz. If it's both divisible by 3 and 5, it should output fizz buzz, like together. Now, a common solution would be to first get the basics out of the way. So that's our validation for loop. um, so let's for loop, right. So we're going to start with our validation loop. So while so we're just going to say valid. We're going to rub this out again. So while valid is false is our next line. We're going to have to ask the user to input. Wait, so we have maximum. And then we're going to test if it's between 70 and 200. So if the variable max is greater than or equal to 70 and it's also less than or equal to 200, so it's valid now. And that's it for the validation, and then we're going to look at these bits here. Then first get our for loop done. So for I in range. So we'll start at 1. And we'll go up to what the user asked for. So with for loops, it goes up to the number just before the second number in this loop here. So we actually want to go to max, what the user asked for, plus 1. Now, what we need to do is we need to check if it's a multiple of 3 or 5 or both. So really, what we should do is check for both first. So if it's to check if it's divisible by a number, we're going to use the modulus operator. And if it's divisible, it should return 0. And we're also going to check if it's also multiple of 5. we're just going to print fizzbuzz. If it's just multiple of 3, so just I modulus 3 is equal to 0, because we now know it's just not a multiple of 5 either if it returns false. The first statement returns false. We print out just fizz. We have another elif statement, because remember you can have as many elif statements as you want. If it's just a multiple of 5, we print out buzz, then else. And so it's not a multiple of both. If it's not a multiple of 3, it's not a multiple of 5. It's not multiple of any of them, so we just print out I. And in the end, what we should get is like something like 1, 2, then fizz, 4, buzz. So like usually you'd write 3 here, but remember it's a multiple of 3. Usually you write 5 here, but it's a multiple of 5 or divisible by 5. Then fizz again, because it's 6, 7, 8, fizz, buzz, 11, fizz, 13, 14, then fizz buzz. That's where our first double hits. And that really is actually a 10 marks. Like fully okay response. Because how the marks are awarded are examiners look for certain things. For example, they'd look for this little loop here for validation. They'd look for this if statement within the validation. That would get you a mark. They'd look for like a boolean for this validation. That would also get you a mark. They'd look for this loop here, print, suitable variable names, correct operations perhaps, if statements, if, elif, else, and so on, outputting the correct thing. And if you just get everything correct, you get a final mark for the program working. However, even though this is okay, it's not the best way to do it, because this FizzBuzz problem has actually been a programming interview question. And I do a few things differently. So if we're going to focus on this bit here, because the thing is, what you don't want to do is you just want to avoid repeating yourself. Because remember, that's what subroutines are for, even. To avoid repeating the same code over and over again. What I'd do is, I'd have, let's say, a few mini lists. So that's our multiples to check if it's divisible by this and then this. And then we're going to have message. We're going to store the string fizz in the first one, then buzz in the second one. We're going to use the same for loop again. Now this time we're also going to start another for loop. So we're going to actually go through each multiple here and then check if it's divisible. So we're going to have another variable name called div, so like where we divide, or if it's divisible. We're going to use in again, but another secret is, instead of range, you could use a variable name if it's a list. So in multiples, So this runs through the list of multiples, 3 and 5. Then if I, so which is still the start, so if this loop controls like each, running through each number, this runs through each multiple, and it tests each time. What we're actually going to do is also, I'm going to sneak in a bit of code here. This is not best practice, but we're going to, not here, right here, output is equals to an empty string with nothing in it. Now back to our second for loop. So this is actually called nested iteration. Now if we're going to check if it's divisible by each bit here, so it's first going to check with 3 if it's divisible, and if it's divisible its modulus is equal to 0. And what we're going to do is output equals plus message. Actually a little change I could do. Could have another counter. So basically, if it's a multiple 3, for example, it will add on this string here, because it's the same index. So this is the first index, or index 0, this is all index 0, 1 and 1, so it kind of matches up. Then once this is done, if output is still an empty string, we know that it's not being divisible by anything because nothing's been added, there's no special words. We just assign it I, and print the output. And the good thing about this is, this kind of takes into account, for example, in interviews, the interviewer might ask you to change a few bits. For example, they might ask you to make it work with 7s easily, which you could just simply change, add another string at the end, and you're done. Whereas rather if you use that AND method, you'd have to check for all 3 and 5 and 7, then just check for 3 and 5, then 5 and 7, then just check for 1 of each. And that's already 1, 2, 3, 4, 5, 6. 6 if and elif statements. And that's going to increase rapidly if we increase like the more number of multiples if it works with. So if we added on 11, it's going to make it more complicated. So that's why some other solutions are better than others. Overall, that's it for Computer Science Paper 1. A few bits at the end, and the additional validation were optional, but are good practice to have when in your GCSEs or beyond GCSEs if you're studying computer science. That's from me, and join me in the next lesson soon. See you soon.